March 1931, Tokyo. Inside a small building at the newly founded Riken Institute for Physical and Chemical Research, a thin man with round glasses adjusted the dials of a machine few people in Asia had ever seen. The instrument was a cyclotron, an early particle accelerator capable of hurling atomic nuclei at tremendous speeds. Its builder, Dr. Yoshio Nishina, was already one of Japan's most brilliant physicists. Trained in Copenhagen under Niels Bohr and a colleague of Albert Einstein, Nishina had returned home convinced that Japan could stand beside Europe and America at the forefront of modern physics. The hum of the cyclotron marked Japan's entry into the nuclear age. In the early 1930s, atomic science was a field of theory more than of weapons. Physicists studied the structure of the nucleus, the strange new behavior of subatomic particles, and the recently discovered quantum laws that governed them. Nishina's laboratory at Riken became the center of Japanese research in the field. There he gathered young scientists, Hideki Yukawa, Shinichiro Tomonaga, and others who would later earn international recognition. They experimented with cosmic rays, radiation, and nuclear reactions, publishing papers in European journals. Japan in those years was changing rapidly. Industrial expansion, imperial ambition, and the rise of the military defined national life. Yet the scientific community still looked outward, exchanging ideas with Western institutions. Nishina corresponded with Bohr and Rutherford, attended conferences, and followed discoveries such as James Chadwick's identification of the neutron in 1932 and Fermi's experiments with uranium in 1934. Each finding deepened his curiosity about the enormous energy hidden inside the atom. By 1937, as war erupted in China and the military gained power in Tokyo, science and nationalism began to intertwine. The Japanese Army and Navy poured funds into laboratories that might produce technologies useful for war: aircraft design, radar, new explosives. Riken, though officially a civilian institute, increasingly worked under government contracts. Nishina's cyclotron, one of only a few outside the West, drew attention from officers eager for technological advantage. In 1938, the global scientific world trembled with a new revelation. Two German chemists, Otto Hahn and Fritz Strassmann, discovered that bombarding uranium with neutrons caused it to split into lighter elements, nuclear fission. Soon after, physicists realized that this splitting released vast amounts of energy. Within months, word of the discovery spread from Berlin to Paris to Washington to Tokyo. Nishina read the reports and immediately ordered his team to replicate the experiment. By the spring of 1939, they had confirmed that uranium atoms, when struck by neutrons, could indeed release bursts of energy and secondary neutrons capable of sustaining a chain reaction. For Nishina, it was a moment of both wonder and apprehension. The equations showed that if such a chain reaction could be maintained on a large scale, the energy released from a few kilograms of uranium would equal that of thousands of tons of conventional explosives. That same year, halfway across the Pacific, a group of scientists in the United States wrote a letter to President Franklin D. Roosevelt warning that Nazi Germany might try to build a bomb using this principle. The Einstein-Szilard letter, delivered in October 1939, triggered the first steps toward what would later become the Manhattan Project. Japan's leadership, however, did not yet grasp the potential. To them, atomic energy remained an academic curiosity. Nishina continued his work at Riken, studying neutron behavior and isotope separation. His laboratory now housed a larger 60-inch cyclotron, the most advanced in Asia. Visitors from the military began to appear more often, asking guarded questions about the possibility of a new kind of explosive. Nishina answered cautiously, emphasizing that theoretical understanding existed, but that engineering such a device would require enormous resources, high-purity uranium, complex machinery, and time. Then came December 1941. The attack on Pearl Harbor plunged Japan into full-scale war with the United States and its allies. The conflict instantly elevated the importance of every possible scientific innovation. Within weeks, the Army's Scientific Research Institute contacted Nishina. They wanted to know whether it was feasible to construct an uranium bomb. Nishina's reply, dated January 1942, was scientifically precise and politically cautious. He explained that fission of uranium-235 could, in theory, produce an explosion of unprecedented magnitude, but that separating uranium-235 from uranium-238 was an immense technical problem. Japan had no large supply of uranium ore, no heavy water production, and no industrial base comparable to that of the United States or Germany. Still, he did not dismiss the idea. He proposed that Riken conduct a feasibility study and preliminary experiments. The Army agreed. Thus began Project NIGO, Japan's secret attempt to build an atomic weapon. The name came from the Japanese word for number 2, reflecting its classification under the Second Army Technical Bureau. Funding was limited, secrecy absolute. The goal was not yet a bomb, but the exploration of isotope separation techniques, gas diffusion and thermal diffusion, that might someday yield enough uranium-235 for a weapon. Nishina's team, about 20 scientists and technicians, worked in a modest laboratory on Riken's Tokyo campus. They built small diffusion columns and tested chemical methods for isolating light isotopes. Every gram of uranium was precious. Japan imported small quantities from captured Chinese mines and from Burma, but the supply was never sufficient. In Europe, the Germans struggled with similar problems. Neither Axis partner knew how far the other had progressed. At the same time, a parallel effort emerged within the Japanese Navy. Led by Professor Bunsaku Arakatsu at Kyoto University, the naval project, later called FGO, focused on theoretical physics and the possibility of using plutonium rather than uranium. Arakatsu had once studied under Rutherford in England and understood the scale of effort required. Yet his laboratory, too, faced shortages and bombings. The two programs, Army and Navy, never cooperated effectively. During 1942, Nishina's group concentrated on measurement and theory. They estimated the critical mass of uranium-235 at roughly 15 kilograms, astonishingly close to modern calculations. Their understanding of fission physics was sound. What they lacked was the industrial infrastructure to produce that material. Even so, reports from Riken circulated through Army headquarters suggesting that Japan possessed the knowledge necessary to design a bomb in principle. For Nishina, the project was not driven by ideology but by curiosity and duty. He had devoted his life to science. Now the state demanded that science serve war. Colleagues later recalled his unease. In private, he told them that building such a weapon might threaten humanity itself. Yet as Japan's situation worsened, he continued the research, hoping that nuclear energy, if not for weapons, might one day power industry and medicine. By the end of 1942, Riken had become one of the most secret facilities in Japan. Guards patrolled its gates. Papers were marked military confidential. Nishina and his assistants kept meticulous notebooks filled with equations and diagrams of isotope separation devices. They submitted periodic progress reports to the Army, noting slow but steady advances in experimental methods. Still, he warned that producing sufficient uranium for a bomb would take many years, far beyond the foreseeable duration of the war. Elsewhere in the world, that same year, the United States consolidated its own nuclear research into the newly formed Manhattan Engineer District, while American laboratories in Chicago and Berkeley began constructing large reactors and enrichment plants. Japan's program remained confined to a few rooms and a handful of scientists. Yet within those rooms, under dim lights during Tokyo's nightly blackouts, the dream of harnessing the atom persisted. The Japanese physicists did not yet know that across the Pacific, their counterparts were racing toward the same goal, but with resources 1,000 times greater. For now, in the winter of 1942, Dr. Yoshio Nishina's vision stood at a crossroads between pure science and total war. The Secret War of the Atom, 1943 to 1945. February 1943, Tokyo. Winter air hung heavy over the capital. The city's streets darkened each night under strict blackout orders, and distant anti-aircraft guns already rumbled as Allied bombers struck targets across the Pacific. Inside the guarded compound of the Riken Institute, however, light still flickered behind reinforced windows. In the basement laboratory, Dr. Yoshio Nishina and his assistants continued their quiet war, not with guns, but with equations and chemical glassware. Their goal was to understand whether Japan could harness the same terrifying power that theory said existed within the uranium atom. The WWII project, now fully under Army control, had entered a new phase. In late 1942, Nishina's preliminary studies convinced the military that an atomic bomb was theoretically possible. What they lacked was a practical means to enrich uranium-235. In early 1943, the Army authorized the construction of a larger experimental facility in Tokyo's Azubu district, near the main Riken campus. There, the team would build prototype separation equipment and conduct tests with small samples of uranium compounds. Every piece of equipment was handmade. Vacuum pumps, diffusion membranes, gauges, all were improvised from materials available in wartime Japan. The nation's industrial system was already stretched thin by aircraft and shipbuilding demands. High-purity nickel and copper were scarce. Electrical power was rationed. Even the glass for experimental tubes had to be salvaged from laboratories damaged in air raids. Yet, the scientists persisted, driven by intellectual ambition and patriotic duty. At this time, Japan's atomic research was divided between two rival institutions, Riken under Nishina and Kyoto University under Professor Bunsaku Adakatsu. The Army funded Riken's WWII project, while the Navy supported Adakatsu's F-GO research. Communication between the two was minimal. Competition and secrecy prevented collaboration. Each side pursued different approaches. Nishina favored gaseous diffusion, Adakatsu explored centrifugal separation and theoretical fission modeling. Neither had access to sufficient uranium ore. The only known source within Japan's sphere of influence was a deposit in Korea and another small site in Burma, both producing only trace amounts. Japan attempted to obtain uranium oxide from Germany through submarine exchange missions. Intelligence documents later revealed that a German U-boat carrying uranium compounds, U-234, was en route to Japan in 1945 when Germany surrendered. It was intercepted by U.S. forces before reaching Asia. In 1943, Nishina's work progressed slowly but steadily. Using small quantities of uranium nitrate, he studied diffusion rates through various materials: nickel mesh, porous glass, even animal membranes. His measurements were meticulous. In one report to the Army's Technical Bureau, he noted that diffusion efficiency remained extremely low, requiring an impracticable large apparatus. He recommended further investment if the military expected tangible results. The Army responded cautiously. Japan's war economy was collapsing under Allied pressure. Resources flowed to aircraft production and the defense of Pacific Islands. Funding for the atomic project never exceeded a few tens of thousands of yen, a fraction of the cost of one bomber aircraft. Still, the officers in charge believed the research might yield long-term benefit, perhaps not a weapon, but a new energy source for the future. Meanwhile, Nishina's personal situation grew complicated. His international connections had made him famous before the war, but now they drew suspicion. The Kempeitai, military police, monitored scientists with foreign ties, fearing espionage. Nishina was respected enough to avoid harassment, but his foreign correspondence ceased. Letters from Bohr or other European colleagues no longer reached Tokyo. Communications were cut by war. Science became an island. By mid-1943, the war had turned against Japan. The defeats at Midway and Guadalcanal shattered the myth of invincibility. Cities were bombed, shipping lines severed, and oil supplies dwindled. Still, inside the Riken laboratories, work went on. The researchers pursued an ever more desperate race, not to win the war, but to preserve their scientific integrity amid national collapse. In August 1943, Nishina completed a report summarizing 2 years of atomic research. It concluded that although the theoretical foundation for an atomic bomb was solid, the material and industrial requirements were beyond Japan's capacity. To produce enough uranium-235 would demand thousands of tons of raw uranium ore, vast electrical power plants, and precision machinery that simply did not exist in Japan's devastated economy. Nishina proposed shifting focus towards fundamental studies of nuclear reactions rather than direct weapon development. The Army, however, still held out faint hope. In early 1944, they allocated modest funds for a pilot plant to test isotope separation at a slightly larger scale. Located in Nishina's Riken complex in Komagome, this plant consisted of several tall diffusion columns and a system of compressors. The installation never operated at full capacity, as bombings and power shortages frequently interrupted work. Nevertheless, it represented the peak of Japan's atomic effort. Parallel to this, the Navy's F-GO project under Arakatsu also pressed forward. Arakatsu's laboratory in Kyoto built a small cyclotron where his students bombarded uranium with deuterons to study nuclear cross-sections. He corresponded secretly with German scientists through diplomatic channels, requesting technical data about heavy water production. German replies, when they arrived, were fragmentary and outdated. Communication between Axis partners had become nearly impossible by sea or radio. By late 1944, the war's end seemed inevitable. American B-29 bombers appeared regularly over Japan, striking industrial and civilian targets alike. Tokyo endured its first large-scale incendiary raids in November. Nishina's Riken compound was hit several times, though the main cyclotron survived temporarily. The scientists began storing data and samples in underground shelters. They knew the institute's days were numbered. In March 1945, disaster struck. A massive U.S. air raid on Tokyo, Operation Meeting House, destroyed much of the city. The Riken Institute suffered direct hits. Fires consumed laboratory buildings, offices, and equipment. The precious diffusion apparatus was melted beyond recognition. Nishina's cyclotron was badly damaged. Decades of experimental notes were lost in the flames. The Japanese atomic project, already fragile, effectively ended that night. Still, Nishina refused to abandon science. In the ruins of Riken, he gathered his surviving staff and began salvaging what little remained. They moved equipment to the countryside and continued small-scale experiments until Japan's surrender in August 1945. By then, the American atomic bomb had already changed history. When news of Hiroshima reached Tokyo on August 6, 1945, Nishina was stunned. At first, he doubted the reports. The initial Japanese broadcast described a new type of bomb with power equal to 20,000 tons of TNT. Nishina knew instantly what it meant. He realized that the Americans had achieved in a few years what he and his colleagues had only theorized. The impossible had become real. Within hours, military officials arrived at Riken, demanding verification. Could such a weapon truly exist? Nishina examined U.S. photographs and radiation data. His conclusion was unequivocal. This is a uranium bomb. He estimated its design accurately, noting that it likely used uranium-235 as the fissionable core. His analysis convinced the Japanese High Command that further resistance was futile. In the days that followed, Tokyo burned again under conventional bombing. The emperor prepared to surrender. Riken's surviving scientists hid their notes and dismantled remaining equipment to prevent confiscation. Some documents were buried beneath the institute's courtyard. Others were destroyed to keep them from foreign hands. When Allied forces arrived after Japan's surrender on August 15, 1945, they found the remnants of once world-class research center reduced to ashes. American intelligence soon learned of the NIGO and FGO projects. The Alsos mission, led by Colonel Pash and physicist Samuel Goudsmit, investigated Japan's nuclear activities. Their report concluded that Japan had understood the principles of atomic fission, but lacked the means to realize a weapon. The total expenditure on Japan's atomic program was estimated to be less than 1/100th of that of the Manhattan Project. In September 1945, Allied officers visited the ruins of Riken. They met with Nishina, who greeted them politely and offered full cooperation. He explained the history of the NIGO project, showed them fragments of destroyed apparatus, and provided surviving records. The Americans, impressed by his candor and intellect, treated him respectfully. Unlike German scientists, such as Heisenberg, Nishina faced no accusations of collaboration in war crimes. His role had been purely scientific. By the end of that year, Allied officers ordered the dismantling of all remaining cyclotrons in Japan. Nishina watched as U.S. soldiers cut his beloved machine into pieces and dumped the remains into Tokyo Bay. It was a symbolic act, the end of Japan's wartime nuclear dream. The destruction of the cyclotron marked not only the end of NIGO, but also a turning point for Japanese science. The war had shown the dual nature of atomic power: infinite potential, infinite danger. For Nishina, it was a personal tragedy. Yet even in defeat, he believed that Japan's future lay in peaceful research. After the bomb, the legacy of Nishina and Japan's forgotten atomic dream, 1945 to 1956. August 1945. Tokyo lay in ruins. The emperor's voice had been broadcast over crackling radios across the nation. Japan had surrendered. In laboratories that survived the flames, exhausted scientists stood among shattered glass and twisted metal. For many, it was not only the end of a war, it was the end of an era of belief in the limitless progress of science. At the Riken Institute, once the pride of Japanese research, Dr. Yoshio Nishina returned to the site where his life's work had been destroyed. The campus at Komagome was a field of rubble. His cyclotron, the machine that had symbolized Japan's scientific modernity, was a heap of warped metal. Yet amidst the ruins, he quietly began to pick up pieces of instruments and fragments of notes, collecting what little survived. In September, Allied occupation forces arrived in Tokyo under General Douglas MacArthur. Their orders were clear: secure all scientific facilities that might have contributed to Japan's war effort, including any work on atomic energy. Within weeks, American intelligence officers from the Alsos mission, who had already investigated German nuclear research, began interrogating Japanese scientists. When they reached Reiken, they were surprised to find the famous physicist Yoshio Nishina waiting for them. Fluent in English and internationally respected, he greeted them with calm courtesy. According to U.S. records, he offered full cooperation and guided the investigators through the wreckage of his laboratory. He explained in detail how Japan's NIGO project had been structured, what equipment had been built, and how far the research had progressed before it was destroyed. The Americans quickly realized that Japan's atomic efforts had been modest and incomplete. Nishina's group had never achieved uranium enrichment beyond laboratory quantities, nor built a working reactor. Compared to the Manhattan Project, which had mobilized over 100,000 workers and consumed billions of dollars, Japan's program was little more than a handful of scientists working with scarce materials. Still, the investigators were impressed by the theoretical understanding the Japanese physicists had achieved under such difficult conditions. Their calculations of nuclear fission, critical mass, and reaction rates were precise. They had grasped the basic principles years earlier, but Japan simply lacked the industrial base to make them real. The Alsos team's report, completed in December 1945, concluded that Japan had made no progress toward a practical atomic bomb, and that its research posed no military threat. The discovery was a relief to American authorities, who feared a potential hidden stockpile of atomic materials. In reality, Nishina's laboratory had barely managed to purify a few grams of uranium compounds before the bombing of Tokyo ended all work. Despite the devastation, Nishina was not arrested or censured. Instead, he became a key advisor to the occupation authorities on the future of Japanese science. The Americans recognized his importance in rebuilding Japan's research infrastructure. In 1946, under Allied supervision, he helped reorganize Reiken into a purely civilian institution stripped of its wartime secrecy. The new organization, renamed the Institute of Physical and Chemical Research, resumed peaceful studies in chemistry, physics, and medicine. However, the occupation authorities imposed strict prohibitions on nuclear research. Between 1945 and 1952, all Japanese work on atomic energy, radioisotopes, and particle physics was banned. Cyclotrons and reactors were dismantled, and even textbooks mentioning atomic theory were censored. Japan's wartime association with atomic research had become a national taboo. During these years, Nishina devoted himself to rebuilding scientific education. He trained a new generation of physicists in general relativity, electromagnetism, and quantum mechanics, subjects safe from political scrutiny. Many of his students, including Hideki Yukawa, who would later win the Nobel Prize in Physics 1949, regarded him as a mentor who bridged the pre-war and post-war worlds of science. Privately, Nishina remained haunted by Hiroshima and Nagasaki. He had seen firsthand the power of the atom he once studied purely for knowledge. After the bombings, he led Japanese scientific teams sent to survey the radiation effects in both cities. His reports, written in late 1945, described radiation sickness, contamination of soil and water, and the long-term dangers of exposure. They were among the first systematic studies of atomic aftermath in Japan. In those devastated cities, he saw not triumph, but tragedy. Standing amid the ruins of Hiroshima, Nishina reportedly told colleagues, "We have entered a world where science and humanity must never be separated again." It was a profound realization that the same curiosity that drives discovery can, under the command of war, bring unimaginable destruction. By the early 1950s, Japan began to emerge from occupation. The Treaty of San Francisco, 1951, restored its sovereignty, and restrictions on scientific research were gradually lifted. A global movement for the peaceful use of atomic energy was beginning, led by the Atoms for Peace initiative of U.S. President Dwight D. Eisenhower in 1953. Japan, the only nation ever attacked with atomic bombs, faced a moral and political question. Should it participate in nuclear research again, this time for peace? Dr. Nishina believed it must. He argued that Japan, having suffered the worst of nuclear war, had a special responsibility to ensure that atomic energy would never again be used for destruction. In public lectures and articles, he advocated for scientific openness, international cooperation, and the development of nuclear power for medicine and industry. He saw in atomic research not a weapon, but a path toward reconstruction. In 1954, Japan's attitude toward atomic energy shifted dramatically. That year, the Lucky Dragon No. 5 incident shocked the nation. A Japanese fishing boat near the Bikini Atoll was contaminated by fallout from a U.S. hydrogen bomb test. The crew suffered radiation sickness, and one man died. The event reignited public fear and anger about nuclear weapons, but it also renewed interest in controlling and understanding atomic energy scientifically. The same year, Japan passed its Atomic Energy Basic Law, declaring that all nuclear research in the country must be devoted exclusively to peaceful purposes. Behind the scenes, Nishina's earlier arguments for responsible scientific development helped shape this policy. Tragically, he would not live to see the full rebirth of Japan's scientific power. On September 10, 1951, Dr. Yoshio Nishina died from a stroke at the age of 59. His death marked the end of an era. In his lifetime, he had seen atomic energy evolve from an abstract theory to the force that destroyed his nation's cities, and finally, to a potential tool for peace. After his death, his students carried forward his legacy. RIKEN was rebuilt into a world-class research institute, and Japan began constructing new cyclotrons and nuclear reactors, all under international oversight. The Japan Atomic Energy Research Institute, JARI, was established in 1956, laying the foundation for the country's modern nuclear power program. In later decades, historians would rediscover Nishina's wartime papers and declassified Allied reports. They revealed how close Japan had come, scientifically, though not industrially, to understanding the principles of atomic weapons. His notebooks showed calculations nearly identical to those of Western physicists, a testament to his genius and to the power of pure research even in isolation. But for Nishina himself, the lesson was not one of lost opportunity, it was one of humility. His final writings, preserved in RIKEN's archives, emphasize the ethical duty of scientists to humanity. The pursuit of knowledge, he wrote, is noble only when it serves life, not death. By the mid-1950s, Japan had begun to redefine its relationship with the atom. Nuclear power plants rose where war laboratories once stood. Radiation research turned from weaponry to cancer therapy. And at RIKEN, a new generation of physicists rebuilt the cyclotron, this time not for war, but for discovery. Today, historians regard Dr. Yoshio Nishina as the father of Japanese modern physics, a man who brought quantum science to Asia, who once tried to build an atomic bomb for his country, and who, after seeing its consequences, became one of the earliest advocates for peaceful nuclear energy. His story embodies the paradox of the 20th century, that the same intellect capable of splitting the atom must also bear the weight of moral responsibility for what follows. From the ruins of 1945 to the laboratories of the 1950s, Japan's journey mirrored Nishina's own, from destruction to rebirth, from secrecy to transparency, from the weaponization of knowledge to its redemption. The atomic dream that began in war ended not in triumph or despair, but in reflection. And in that reflection, the world learned a lasting truth: that the power to shape history lies not in the atom itself, but in the conscience of those who seek to understand it.